An ant just lost its leg. What happened next should be impossible. An ant loses a limb in battle. In less than 60 seconds, its sisters find it. They surround it. They carry it home. And then, and I want you to really hear this, they perform surgery on it. Not metaphorical surgery, not instinct, actual deliberate surgical amputation, where other ants chew through the damaged limb to stop an infection from killing the patient. Now here's the question I need you to sit with for the next 17 minutes. For an ant to choose to save another ant from pain, does the ant have to feel pain itself? Because if the answer is yes, and I'm going to show you the evidence that suggests it is, then we have been stomping on creatures capable of suffering for our entire lives without a second thought. And science, right now, is sitting on one of the most uncomfortable realizations in the history of biology. To understand what's really going on inside an ant when it's injured, we need to start where scientists start, with the hardware. The ant has a brain. It's about the size of a grain of salt. And for over a century, scientists looked at that tiny grain of biological material and said, there's nothing in there capable of feeling anything. They were wrong. Here's the thing about the ant brain that will completely change how you think about it. Yes, a human brain has 86 billion neurons. An ant has between 50,000 and 250,000. That sounds like a laughable comparison, until you look at the density. If you scaled an ant brain up to the physical size of a human brain, it would contain over 500 billion neurons, more than 5 times the density of yours. 5 times denser. Now you might be thinking, okay, density is interesting, but density doesn't mean feeling. And you'd be right to push back on that. So let's talk about what actually creates the experience of pain. There's a critical distinction that most people, including most non-specialists, completely miss. There's a difference between nociception and pain. Nociception is the plumbing, the pipes that carry a danger signal from your skin to your brain. Even a single-celled organism can have nociception. It moves away from a needle. That doesn't mean it suffers. Pain, real pain, is what happens when that signal arrives somewhere in the brain that processes it as unpleasant, where it gets colored with emotion, where it becomes something the animal wants to stop. So the real question isn't, do ants have nociceptors? They do. We knew that. The real question is, where does that signal go? And here is where it gets deeply uncomfortable for anyone who assumed ants were just biological robots. The ant's nociceptors, its danger sensors, are wired directly into a region of the brain called the mushroom bodies. And the mushroom bodies are the seat of learning, memory, and sensory integration in insects. It's the closest thing an ant has to a cortex. So when an ant's leg is crushed or burned, the signal doesn't just trigger a twitch. It goes to the part of the brain that remembers things, that evaluates things, that can decide what to do next. Now you might be thinking the obvious counter-argument. Scientists have thought this too, but ants don't have a neocortex. Humans feel pain in the neocortex, so ants can't feel pain. And for decades, that argument won. Case closed. Ants are machines. But modern neuroscience has a term for that logic, the neocortex fallacy. The idea is called multiple realizability, the principle that nature can achieve the same functional outcome through completely different biological structures. A jet engine and a bird's wing both achieve flight. They look nothing alike. Neither is wrong. An ant's mushroom bodies might achieve subjective experience through a completely different architecture than our neocortex. Different hardware, same output, which means the question is no longer can ants feel pain. The question is, what's the evidence? Scientists have developed 8 criteria for determining whether an animal can experience pain. Not guesswork, a rigorous marker-based checklist. Let's go through what ants score. Criterion 1, nociceptors. Do they have the sensors? Yes. Ants have nociceptors on their antennae and legs tuned to detect extreme heat, crushing pressure, and caustic chemicals, the same thresholds that trigger pain in mammals. Over 40 degrees Celsius, the sensors fire. Criterion 2 and 3, integration and neural pathways. Does the signal go somewhere meaningful? Yes, straight to the mushroom bodies, as we just established. The wiring is there, the destination exists. Criterion 4, analgesia. This one is haunting. If you give a human morphine when they're in pain, they feel better and they act better. Less distress, more normal behavior. Researchers tested this on injured insects. When given painkillers, actual analgesic compounds, injured insects returned to near normal behavior. The painkiller worked. But it gets stranger. Ants don't just respond to painkillers. They will seek them out. Ants self-administer morphine. In controlled experiments, ants given access to morphine-laced food preferentially chose it when injured. They understood, on some level, that the substance reduced something unpleasant they were experiencing. That is not reflex behavior. A thermostat does not go looking for an ice pack. Criterion 5. Motivational trade-offs. Will an animal endure harm for a reward? Yes. Ants will walk across surfaces heated to painful temperatures to reach food. They weigh the cost. They make a choice. Criterion 6. Flexible self-protection. The surgery chapter. This is the one that ends the debate for many researchers. Let me walk you through it carefully. The Matabele ant of sub-Saharan Africa specializes in raiding termite nests. These raids are brutal. Termite soldiers fight back, and Matabele ants frequently lose limbs. When an ant is injured in battle, something extraordinary happens. It releases specific chemical signals from its mandibular glands, compounds called dimethyl disulfide and dimethyl trisulfide. A chemical SOS nestmates detect these signals. They come to investigate. And then, and this is where it stops being just instinct, they perform triage. Ants with minor injuries, 1 or 2 legs lost. They get picked up, carried back, treated. Ants with catastrophic injuries, 5 or more legs gone. They resist rescue. They flail. They refuse to cooperate. They effectively communicate, "Don't waste resources on me." And here's the detail that will stay with you. Lightly injured ants behave more injured when near their nestmates, moving slower, falling over, to make sure they get noticed and helped. But when researchers observed the same ants in isolation, they ran perfectly well. They were performing vulnerability to get help. That requires a theory of mind. It requires knowing that others can see you. It requires wanting something, relief, badly enough to manipulate your environment to get it. And then in 2025, it went even further. Researchers studying carpenter ants discovered that nestmates don't just treat wounds, they amputate limbs. If an ant's leg is too damaged to heal, infected, gangrenous, other ants will systematically, deliberately chew through the limb to remove it. Prophylactic amputation. The exact same logic a human surgeon uses when removing a gangrenous limb before the infection spreads to the body. The ants are performing a cost-benefit calculation. Lose the limb, save the life. That is not a reflex. That is medicine. Criterion 7. Associative learning. Ants learn to avoid locations where they've been hurt. Not just once, persistently. The memory of harm shapes future behavior. That is the emotional signature of pain, not mere nociception. Criterion 8. Analgesia preference. Already covered. They choose the painkiller. They seek relief. 7 out of 8 criteria. Researchers using this framework concluded the evidence is, and I'm quoting directly here, substantial. The chemistry of suffering. One more layer before we get to the big conclusion. The chemistry. When a human is injured, the body floods with cortisol and adrenaline. The whole internal state of the body changes. You don't just detect the damage, you feel urgency, distress, a drive to make it stop. Ants have a parallel system. Their primary stress compound is octopamine, the invertebrate equivalent of noradrenaline. It floods the system under threat. It heightens aggression. It prepares the body for fight or flight. And dopamine, yes, the same dopamine you have, fluctuates in ants under injury and threat, mediating risk assessment and behavioral choices. Their internal chemical state is profoundly altered by harm. Different molecules, same function, same outcome, multiple realizability. Again, now I want to step back from the data for a moment, because I think there's something more uncomfortable here than the science. We've spent centuries building a worldview where the line between things that matter and things that don't was drawn around creatures that look like us. Creatures with faces. Creatures with eyes we can read. Creatures whose suffering we can recognize because it resembles our own. Ants don't look like they're suffering. They don't scream. They don't curl up. They keep moving. They keep working. And we interpreted that as evidence of emptiness. But evolutionary biology tells us exactly why that is. In the insect world, showing weakness is a death sentence. An ant that stops and writhes in pain gets eaten. So the ones who survived, the ones whose genes we're looking at now, were the ones who kept moving through the pain. Their stoicism is not evidence of absence. It is the product of 130 million years of brutal natural selection that said, feel whatever you feel, but never let it show. And if that realization doesn't make you sit differently the next time you see an ant on the pavement, I'm not sure what will. Jonathan Birch, a philosopher of biology at the London School of Economics, has said the evidence for insect sentience is, and this is his word, uncomfortably strong, not strongly proven, uncomfortably strong, because the implications are enormous. The UK's Animal Welfare Sentience Act in 2022 began recognizing invertebrates, crabs, lobsters as sentient. There is now active scientific lobbying to extend that to insects, to ants, to bees. The precautionary principle is now the guiding framework for many researchers. If we aren't sure they can't feel pain, we should act as if they can. Here's the thing about the question, do ants feel pain? It was never really about ants. It's about where consciousness lives. It's about whether the universe contains more suffering than we ever accounted for. It's about whether the line we drew between mattering and not mattering was ever based on truth or just on convenience. A colony of 40,000 ants contains roughly the same total number of neurons as a single human brain. When one ant is hurt, chemical signals ripple through the colony. Others respond. The body of the superorganism reacts to the wound. Maybe the individual ant isn't the right unit of analysis. Maybe the colony is the organism, and the individual ant is more like a cell in your skin, carrying out its function, sending signals, part of something vastly larger than itself. Darwin called the ant brain an atom of matter, meaning something almost impossibly small, but still real, still there, still doing something. In the coming years, as scientists map the full connectomes of these animals, the complete wiring diagrams of their nervous systems, the line between us and them is going to keep blurring. Not because ants are going to start seeming more human, but because consciousness itself, the thing we assumed was uniquely, exclusively ours, is turning out to be far older, far more widespread, and far more distributed across life than we ever wanted to admit. So, do ants feel pain? The honest answer, right now, in 2025, is this. We cannot say for certain that an ant experiences agony the way you or I do, but we can say, with substantial, peer-reviewed, replicated scientific evidence, that they have the hardware to detect harm, the chemistry to be distressed by it, the memory to be shaped by it, and the social behavior to do something about it. That is not nothing. That is, by most reasonable definitions, pain. The atom of matter, it turns out, has been feeling things all along. We just weren't paying attention. Until now. If this changed how you think about the smallest creatures sharing this planet with you, that's exactly what this channel is here to do. Drop a comment with the fact that hit you hardest. And if you want to go deeper, the next video covers how scientists are now mapping insect consciousness. And what they're finding is even more unsettling than this.